Swayam Prabha. Digital India. Educated India.
Good morning. So in the last class, I had discussed about writing mass transfer expressions. We have two choices. One is we could write NA using the local mass transfer coefficient Ky, where here the driving force is the YAG minus YAI. So that's a driving force for mass transfer in the gas phase. Now, if you want to avoid the use of interfacial concentration, we can think about using a different kind of a driving force, YAG minus YA star. And with the new coefficient, which is called the overall coefficient, overall mass transfer coefficient in the gas phase, based on the gas phase concentrations. And the advantage of using this YA star as a driving force is that since we know the equilibrium line, we can calculate YA star, which is in equilibrium with, this is in equilibrium with XAL, which is right here. So since we know YAG and XAL, corresponding to this liquid phase composition XAL, using the equilibrium line, we can obtain YA star. Then we can use YAG minus YA star as a driving force to calculate the flux, in which case we have to use an overall mass transfer coefficient, capital KY. And I also showed the relationship between the overall mass transfer coefficient and the local coefficients using the line that joins the this point and this point, okay, which is M prime. Okay. So now we can show that whether you use local coefficients or the overall mass transfer coefficients with the different driving forces, the flux that you calculate will be the same. Okay. So if I go back to this particular problem which I solved in the last class, we can now calculate, since I know Kx, Ky and M, I can calculate what is the overall mass transfer coefficient. So 1 by Ky is equal to 1 by small ky plus M prime by Kx. So this becomes M prime is 3, Kx is 3 into 10 power minus 3. If you solve this, you will get 167. And then you can invert this to get Ky, and you will get 6 into 10 power minus 4. The same unit of Kx and Ky. Now with this overall mass transfer coefficient Ky, we can define the flux. So now I know this, I also know this, I need to calculate this YA star. So to calculate YA star, I use the equilibrium line, which is 3 XAL. Okay. So I'm using here the bulk concentration XAL, because I know that YA star is the one that is in equilibrium with XAL. So I'm using the equilibrium relationship Y equal to mx and substitute for XAL in that equation, then I get YA star. So this will be 3 times XAL, which is 0.05. So now we can calculate Na. So this is 6 into 10 power minus 4. YAG is 0.8 and YA star is 0.15. And this gives you a value of 3.9 into 10 power minus 4 kilomole per meter square second. So this is the flux we also got using local coefficients and interfacial concentrations. So the objective of this example is to show that you have the choice to make either use a local mass transfer coefficient and interfacial concentrations, or use the overall mass transfer coefficients and the driving force relating the bulk concentration and the equilibrium concentrations. These are the choices. Now what we have just done with regard to the gas phase mass transfer coefficient and driving force, we can do the same thing for the liquid phase also. Okay, meaning we can also write the flux based on the liquid phase composition Na using the mass transfer coefficient small kx xai minus xal. This would be based on the driving force xai minus xal using the local coefficient kx. Or equivalently, we can try to write this flux in terms of xa star minus xal with a new coefficient kx, capital Kx. So this xa star is somewhere here. This xa star is the liquid phase concentration in equilibrium with the YAG. Okay, YAG is the gas phase bulk concentration. Corresponding to that, there will be an equilibrium liquid phase composition which can be obtained from this equilibrium line. Just like how we obtained the gas phase equilibrium concentration corresponding to XAL, same way you can calculate the liquid phase equilibrium concentration corresponding to the gas phase bulk concentration YAG. And we can also see in this case that XA star minus XAL is the overall driving force given by this particular line, can be decomposed into two parts, XA star minus XAI plus XAI minus XAL. Now from this definition of mass transfer rate, XA star minus XAL can be written as Na divided by capital Kx. This one is based on the local mass transfer coefficient. So Na divided by small kx. So this XAI minus XAL can be obtained from the local coefficient. So you will get Na divided by small kx. Now this is a new term which corresponds to this particular difference, XA star minus XAI. To find this out, we are going to use another line that connects these 2 points, and we will say this slope is m double prime. Okay. Suppose if this equilibrium line is a straight line, both m prime and m double prime will be the same. However, depending upon the temperature and operating condition, the equilibrium line need not be a straight line always. It can have a local curvature. So we can define a different slope m double prime. But as we will see later on in many problems, m prime, m double prime are typically the same because the line is a straight line. But to keep generality, we will assume that this particular line has a slope of m double prime. So with this, we can now write XA star minus XAI as YAG minus YAI by M double prime. And we already know that YAG minus YAI can be also written as NA by small ky times N double prime. Now we can take out all this Na here, so we'll have 1 by Kx is equal to 1 by Ky times M double prime plus 1 by Kx. So this is the overall mass transfer coefficient based on the liquid side compositions. So these are two alternative ideas. Either we can use this capital Ky, which also requires this knowledge of small kx, small ky and m prime, or we could use this capital Kx using small kx and small ky and this slope of the line connecting this part of the equilibrium line. Now the reason to write this overall coefficients and local coefficient is so helpful because it allows us to analyze where the overall mass transfer coefficient is limited. Is it on the gas side or is it in the liquid side? This is something you might have done in heat transfer course also, where you define overall heat transfer coefficients using the two local coefficients on the inner side and outer side. Okay, and then you look at where the major resistance lies, and then if you want to improve the overall heat transfer coefficients, you know what to do, which side of the heat transfer coefficient has to be enhanced so as to reduce the resistance. In the same way, here also we can discuss about the relative resistance of mass transfer on both phases. Okay, so the way I have written 1 by ky as 1 by small ky plus m prime by capital small kx. So this basically says about overall resistance. This is basically the inverse of the mass transfer coefficient. In heat transfer, you would have defined this 1 by capital U, which is the overall heat transfer coefficient. So here we are just replacing the heat transfer coefficient with the mass transfer coefficient, and this is the resistance in the gas phase. This term together is the resistance. When I say resistance, is resistance to mass transfer, resistance in the liquid phase. So if you want to analyze what fraction of resistance lies in gas phase or in the liquid phase, you can say resistance in the gas phase over the total resistance is equal to 1 by ky small ky divided by 1 by capital Y, which basically becomes this. So if I know the individual values of kx, yeah, denominator is 1 by ky. Oh, here I have written kx, is it? Okay, I see. Yeah, this should be y, yes. So if I know the individual values of ky and capital Ky, this ratio will tell you what fraction of the resistance lies in the gas phase. Similarly, if you want to know what is the resistance in the liquid phase, over the total resistance, this would be m prime by kx by 1 by ky, or other words m prime ky by kx. Okay, this will be in fractions. Okay, and you can assess which resistance is dominating. This is based on capital Ky. You can do the same thing with the liquid phase overall mass transfer coefficient also. So suppose if you are given with capital Kx, small ky and small kx, in this case also you can ask what is the resistance of the respective phases. In this case, resistance in gas phase over the total resistance is 1 by m prime double prime ky by 1 divided by kx, or kx over this. Similarly, resistance in liquid phase over total resistance is 1 by small kx by 1 by capital Kx. Now, if you go to this particular case, you can see that if you have m prime to be very small, okay, suppose if m prime here in this equation is very small, what it means is it tells you about your equilibrium line. Okay, so you have an equilibrium line which has a very small slope, something like this. Remember, the slope of this equilibrium line is m prime. Like I said before, I am taking this as a straight line, so m prime, m double prime will be the same. Okay, so when you have this kind of a very small m value, what it means is that a very small change in the concentration of y will lead into a large change in the concentration of x. That's what the smallness of m means here. Okay, so if we change the composition of the gas phase a little bit, at equilibrium the liquid phase composition will change quite over a broad range. Okay, so such a case we call it as a very soluble gas. So the solute in the gas phase is very highly soluble in the liquid phase. That's what this means. Okay, if you have such a situation where the slope of the line is very small and the gas is highly soluble in the liquid, you will see from this equation this term is actually negligible. It's vanishingly small, and that basically brings us to the case that the overall resistance actually lies in the gas phase, because the liquid wants to absorb the gas very fast, very easily, because it's very highly soluble. So you're not expecting any resistance in the liquid phase at all. So majority of the mass transfer resistance now comes from the gas phase. Okay, so that's the implication, physical implication of the slope of the line being very small, right? Now, if you come to this particular case, you can have a case where this m double prime here, again m double prime are the same thing. You can have a very high value, which means the line goes something like this. Okay, here I am talking about a totally different gas liquid system with a very high slope. Okay, so what this means here is, if I change the composition in y to a large extent, that shows a very small change in the liquid phase composition. So here we call this gas is sparingly soluble or insoluble. Okay, even if you change the gas phase composition drastically, the corresponding liquid phase composition will only change a little bit, because the slope of the line is very high. The slope of the line dictates the equilibrium solubility of the gas in the liquid. Okay, so such a case we call the gas is, this is sparingly soluble gas. So from here in this equation you can see, when m double prime or m is very large, so clearly it means that the resistance in the gas phase is now vanishing. Okay, and much of the resistance now comes from the liquid side, because the solute does not want to be solubilized in the liquid. So the liquid actually offers the major resistance to the mass transfer. Okay. So by looking at the solubility curve, whether it has a lower slope or very high slope, you can tell, you can make an intuitive guess that where the major resistance might lie. Okay. When I do this analysis about the slope being very high or low, that means whether it's sparingly soluble or highly soluble, I am also making an assumption that the kx and ky are of the same order of magnitude. Okay. But if kx and ky vary drastically depending upon the mass transfer equipment you have, different kind of flow conditions you have, kx, ky may be either of the same magnitude or they can widely vary also. The analysis about m prime being small or large is with an assumption that the kx and ky are of similar magnitude, then I can drop out one of the term and focus on the other term. Okay. So generally we give kx, ky equilibrium line and we ask you to calculate where is the major resistance lie. Okay. Why is it important to know where the resistance lies? Why is it important to analyze that? Yes, if I know which phase is limiting the mass transfer, I can focus my attention to increase the flow conditions, mixing conditions, or various other possibilities we have so as to enhance the mass transfer rate. So we don't have to unnecessarily, for example, in this case, when I am looking at this sparingly soluble case, there is no point doing increasing mass transfer in the liquid phase, right? So you have to always work on the phase where it offers the major resistance so as to improve the mass transfer coefficient. Okay, so that's why it's very important to analyze where the major resistance lies. Now, if based on this equilibrium line slope and then we understand where the major resistance lies, what we are able to then do is we are able to actually say, for example, if gas phase is controlling, then we say that this ky is very similar to small ky, right? So this also means that this driving force YAG minus YA star, this driving force is actually almost same as this. Graphically what this means is, here I showed YAG is here, YA star is here, so the differences are different. YAG minus YA star is much higher than the YAG minus YAI. But if the slope of the line becomes very small, this YAI and YA star will come close to each other, right? Let me just draw that here. So if I have y versus x and I have a line which is very small in slope, my point P is somewhere here corresponding to YAG. This point here that cuts the equilibrium line is YA star and my YA may be somewhere here. Okay, this is my line that is governed by minus kx by ky. This is the driving force line. So you can see this YI now has come very close to YA star. The line M, the equilibrium line with M being very small basically means this interfacial concentration now comes very close to YA star itself. So whether I take this particular driving force or I take this driving force, they are essentially the same, right? Because the interfacial concentration will be very close to the equilibrium concentration. So I can change the overall driving force is equal to YAG minus YA star. In other words, I can use the total resistance ky, total mass transfer coefficient ky is equal to small ky. And you can say the same thing about the gas liquid phase controlling. Suppose if liquid phase is controlling, then we noted that the scale will be very similar to small kx. Okay, in other words, the driving force XA star minus XAL is almost same as XAI minus XAL. So graphically it can be shown like this. So I am going to draw a line that has a very high slope, something like this. So my point P is here, corresponding to YAG, and this is XAL, and this is my YAI, this is XAI, and I am going to calculate this XA star based on the equilibrium line. So you can see that XAI now is very close to XA star. So instead of using the interfacial concentration, I can very well use the equilibrium concentration. Okay. The fact that M is very high basically means the interfacial concentration and the equilibrium concentrations are very close by. So the idea I am trying to say here is that when you look at mass transfer of a solute across two phases, you have to deal with mass transfer resistance in both phases. You have to get the mass transfer coefficient in both phases, and then you decide which phase is offering more resistance. Okay, by doing this analysis, it depends on the system in question. It also depends on the equilibrium line in its how what's the curvature of the equilibrium line. Okay, so based on this analysis, you can tell which phase is offering more resistance. So generally, if you look at the mass transfer coefficient of the liquid side or a gas side, the liquid side would have lot more temperature dependence. Okay, that's because the liquid phase properties are very much temperature dependent. The diffusivities, the viscosities, the densities, these are quite strong functions of temperature. So when you do a mass transfer study and you see a large difference in the temperature, suppose if you change the temperature, you see a larger change in the mass transfer rate, it's an indication that your liquid phase is controlling. Okay, compared to the gas phase mass transfer coefficient, liquid phase mass transfer coefficients are far more influenced by temperature. So you can make an intuitive guess that whenever there is a mass transfer rate enhancement by temperature, it is very likely that it is a liquid phase controlling. And vice versa also is true. You keep working with different temperatures, but the mass transfer rate is not changing very much. It may be that the gas phase is controlling. Here I have drawn this as an equilibrium line with a straight, So what happens is, if you take Raoult's law or Henry's law, these are all equilibrium lines with a straight slope, which is true for very dilute mixtures. You know, if the concentrations are not too high, you're talking about solute in the range of 1% or 2% of the total composition. So then you can work with the straight lines. If you go to very highly concentrated mixtures, where the non-ideality will come, the composition are very high, so the equilibrium line can actually become curved. The analysis become very easy if you consider them. Otherwise, you have to deal with the two different slopes and then compare. But the idea is the same. I mean, I can give you a kind of a curved equilibrium line, and then for those particular interfacial concentration and the equilibrium concentration in that particular segment, you find the slope. You can define the slope along the curve, and then you can decide. So I'm talking about two different classes of gases. One is very sparingly soluble, another is very highly soluble. They can be characterized based on a different slopes. So are these new concepts or something you've already learned in fundamentals of heat and mass transfer? New? Not new. Okay. So they're familiar to you. Now, what I want to do is next is again, you might have already noticed that I'm using different kinds of mass transfer coefficients. There is this small kx, small ky, capital Kx, capital Ky, capital Kl, and there are more to come. Okay, this is because the way, suppose if you look at heat transfer, okay, so there the heat transfer is proportional to the temperature difference, and temperatures are measured in terms of Kelvin, Celsius. Okay, that's all. But then when you come to mass transfer, here the driving force is composition difference, okay, or chemical potential difference. Now if you write in terms of composition, then we have so many units to use. I can use mole fractions, I can use mole ratios, I can use concentrations itself, moles per unit volume, or I can use partial pressure, right? There are so many ways to write it. But the mass transfer flux will have a fixed unit. It will be always in moles per unit area, unit time. So if the flux is given in the same unit, and if you change the units of the driving force, then obviously the proportionality constant in this case, which is mass transfer coefficient, will have different dimensions, different units. And it's for great confusion when you look at mass transfer coefficient reported in some way, whereas you want to use it in some other forms. Okay. In other words, I'm going to discuss in detail how these mass transfer coefficients are related to each other. Given one form of mass transfer coefficient based on particular driving force units, how can I write that into another form? Okay, this is very important because the reported literature, the mass transfer coefficients reported in literatures would be based on some experiments, and they would have a free choice of choosing different concentration units, and they will report mass transfer coefficients based on this particular concentration units. Whereas for the problem in your hand, you may be working with the different units of concentration, and you have to change the units of the mass transfer coefficient wherever you need. Okay, so therefore it is very important that we understand what is the relationship between the mass transfer coefficients. Okay, so in doing this, I'm going to again brush up some of the fundamentals of mass transfer you have already studied. Many of the things will be very familiar to you, but anyhow, for the purpose of refreshing it, we will do it. And my point is to show the connection between different kinds of mass transfer coefficients, and end of this modules, you should be able to convert mass transfer coefficient given in one units to something else, to some other units. Okay, so this section will be on mass transfer coefficients. So we'll start from very fundamentals. Okay, so we'll write the so in mass transfer we write the flux is equal to the total flux times the mole fraction plus the diffusion flux JA. For binary system, we can write this as N is Na plus Nb, Xa can be written as some ratio of the Ca by C, and Ja is dAb dou Ca by dou Z. So here I am writing one dimensional diffusion equation based on fixed law. And so now what you can do when you're looking at this, so we are looking at one dimensional diffusion. Here this Z here is the one dimensional direction, and Ca is the concentration of the solute A, and B and A, these are the two components. Okay, binary mixture A and B. So what we can do at steady state, the diffusion is happening such a way that Na and Nb are actually constant. So then what we can do is we can rearrange this. So if you integrate this, So you can write now that this flux Na is related to these set of terms, and we call this particular group of terms as F. This is a local mass transfer coefficient. This is called as F type mass transfer coefficients. Okay, so we have Na as Na by Na plus B F times ln of this term. So this is more like a general case for two binary mixture A B, and so from here onwards, we if you want to simplify this further, we deal with two cases. One is A is diffusing through non-diffusing B, or both A and B are counter diffusing. So these are two cases that we often encounter in mass transfer. In the case of A diffusing through non-diffusing B, can you think of any example of a mass transfer process? Where do you expect A diffusing but B is not diffusing in terms of mass transfer operations? No, tell me in terms of operations like absorption, distillation, drying, humidification. We looked at a lot of examples, right? Absorption, humidification, drying, these are all the cases where only one solute is diffusing, the other solute is inert. On the other hand, if you look at the fractionation like distillation, where both components will be diffusing back and forth. Okay, so most of the mass transfer operation can be classified into these two kinds: A diffusing through non-diffusing B, or both A and B counter diffusing. And these are two special cases for which we can simplify this expression even further. Okay, for example, let's take diffusion of A through non-diffusing B. What this means is your NB is 0 because B is not diffusing. Okay, so then you can see this expression simplifies to like this. Yeah. Huh? Yeah, I'll explain this. So this expression is for all combinations of A and B diffusing, or B is diffusing, etc. So if I apply this to a diffusion of A through non-diffusing B, then the flux NB is actually 0 because B is not diffusing, only A is diffusing. So this term Na by Na plus Nb will become just 1. So you got Na equal to this F times, this term becomes 1 minus Ca2 by C, this becomes 1 minus Ca1 by C. Okay, and then if you rewrite this, you should be able to write C minus Ca2 by C minus Ca1. So if you apply this for a gas phase, concentrations are written in terms of pressures, right? For example, C can be written as total pressure by RT. Okay, or if I want to write Ca1, I can use the partial pressure of A1 by RT, or Ca2 is partial pressure by RT. Okay, so these are things that are happening at constant temperature and constant pressure. Okay, so when you look at this A diffusing through non-diffusing B, if you look at between two places Z equal to 1, Z1 and Z2, what will happen is, so C1 is coming from Ca1 to Ca2, correspondingly the CB1 will increase from CB1 to CB2, right? So this is because the total has to be always same. The concentration Ca1 plus Ca plus Cb has to be constant at all times in this spatial location. Okay, when A is decreasing as a function of Z, correspondingly Cb will have to increase so that the total pressure or the total concentration remains constant. Okay, because of this fact, what I'm able to write here is, so from here to here, I'm writing Ca minus Ca2 as Cb2, C minus Ca1 is Cb1, because the sum of the concentration should be equal to C at any point. Okay, so further what I'm trying to do here is, I'm also introducing this term Ca1 minus Ca2 by Cb2 minus Cb1, because the numerator and denominator, they are actually equal. Okay, because if you look at this difference, will be exactly same as the difference between these two. The extent by which A is changing and to extent B is changing, they have to match so that the total concentration remains equal, constant. Okay, so I'm making use of that particular property and I'm able to write this. The reason why I'm writing this, because since I have this ln of Cb2 by Cb1, if I have this term Cb2 minus Cb1, I can group these two terms and write in terms of logarithmic mean difference, a logarithmic concentration difference of B. This is something you might have studied in heat transfer also. You study what is called this logarithmic mean temperature difference, LMTD. In the same way here, for the species B, we are defining a logarithmic mean concentration of B. Okay, so this CBM that is defined here is Cb2 minus Cb1 by ln of Cb2 by Cb1. Everything is related to component B. Okay, even though we are interested in mass transfer rate with respect to A diffusing, B's concentration is also changing, but we don't want to account for its change, so we want to kind of normalize its change into a one single factor, which we call this a logarithmic mean concentration difference for component B. Okay, so the advantage of doing this is that I can group all these terms together and then write as CBM. The coefficient F remains so, and then now I am writing Ca1 minus Ca2. Ca1 minus Ca2 is the concentration difference between the two locations Z1 and Z2. Now, and if I have already noted that this F coefficient is nothing but DABC by Z, and then so you have this expression. So what we have done, let's go back here. What we have done, So you have taken this general expression for the flux, and I'm simplifying this for A diffusing through non-diffusing B, and by making use of this conservation of this concentration or pressure in this case, I'm able to write the flux in terms of concentration difference. If you look at the original expression, the concentrations are involved in the logarithmic term. It's difficult to work with logarithmic terms. It would be nice if I can write in terms of concentration differences as a driving force. Okay, so we are able to simplify the original expression for the flux in terms of the concentration difference between two locations. Now you can relate this to the way we have written mass flux in the previous module, where we wrote some local coefficient times the concentration difference or mole fraction difference. Mass transfer rate as some coefficient times the concentration difference can actually be derivable from the fundamental laws of mass transfer also. Now you can see the relationship between the coefficients. Here we have defined, we didn't use concentration units, but you used compositions, but you could also write this Na as Ky into Ya1 minus Ya2 also. Okay, we will come to this, but let's say since here we are using concentration unit, here also we are using concentration unit, the prefactor has to match. So therefore we can say the coefficient F by CBM is actually equal to Kc. This is an exact relation. Sometimes you are given with this mass transfer coefficient F through some correlations, but you may want to get small kc because you want to work with this kind of a mass transfer rate, and this is an equation where you can relate the two mass transfer coefficients. To do this, you have to know what is the logarithmic mean concentration difference of component B. Once you know that, you can relate this. Now this is a very general approach. Now you can change the concentration units. For example, instead of concentration, you can work with partial pressure, okay, by changing C equal to P by RT. Then you get concentrations expressed in terms of partial pressure. The prefactor will be different now. Then you match this with the phenomenological mass transfer rate using this kind of an expression, and then you can match the coefficients. Then you can get set of mass transfer coefficient relationship between what is known and what is given. Okay, so in view of time, I'll stop here. In the next class, I'll continue further for equimolar counter diffusion also, and then take commonly used concentration units like mole fractions, mole ratios, partial pressures, and then relate the coefficients. Okay, when we do some numerical problems, we'll be faced with this particular challenge of converting the units of mass transfer coefficient, and it's important that you know how to do it.